cover something else apart from this. We can also discuss at the end of this presentation. Right. So, as you know, right, I mean, electronics industry has achieved a phenomenal growth over the last few decades. It's mainly due to the rapid advance in the large scale integration technology and the system design application. Way back in 1959, it started with the single transistor, and the density of that transistor is just one. Now, if you see after that, the SSI come, the small scale industries come, and then the density goes increase in 1964, then MSI, LSI. Now we are talking about the VLSI. Now, on top of the VLSI, also there is a ULSI, right? So ULSI is also come around late 90, and it was a more than 10,000 density number of gates. And then now we are talking about the SoC. So SoC is nothing but the system on chip. That means you have a one system, and that system has each and everything. It doesn't have only just transistors or MOSFET or resistors or capacitor. It has a processor, it has a subsystem, it has a memory. All these things, what you can imagine, that can be part of my single chip. And that is started in the late 90s, or I would say early 90s. And the number of gates that we were coding in a single chip, which was like more than 10 million. So when I joined industry in 2006, at the time my first project was, we were working on the one of the complex chip in a Texas Instrument, which was going into the mobile processor, and that chip had a almost 11 to 12 million gates into the single chip. Now whatever the chip that as of now the industry is building, uh, definitely the mobile chip is complex, and then there is a microprocessor or microcontroller. Microcontroller is relatively less complex chip compared to the mobile chip. On top of that, there is a server chip, which is a giant and the biggest chip, I would say, on the planet, which has almost 20 billion gate. I'm not talking about the millions, but I'm talking about the billions. So as of now, and that too in a technology which is advanced in edge cutting. So we are working on a 7 nanometer, 5 nanometer, 3 nanometer. So as the technologies goes, the number of transistors you can accommodate, the number of CMOS gates you can accommodate per mm square is much more higher, right? And with those latest cutting edge technology, we are in a position to accommodate more than 20 billion gate. So the sky is limit. Somewhere, sometime, some years back, I read one of the article, and in that article, it was written, whatever the growth is happen in the VLSI industries, if the same growth would have happened in the automobile industries, then maybe the Maruti cars would have cost only just $100 rather than in terms of lakhs. It would have cost just $100, means few thousand rupees, right? So the growth is happen in VLSI is amazing, and sky is the limit. Every day we are seeing a lot of growth. So same way, I think in the first session, the other speaker must have cover what are the different applications, but I just wrote it down, what are the different application of the digital design. So you just name it and there is a digital design, right? So it may be a satellite, it may be a space, it may be a fiber communication. So we are delivering lecture, we are not physically apart, we are physically far away, and still we are able to listen each other, we are able to see each other, right? So again, it is based on the fiber communications, and where there is a digital design. Smartphones, smartwatches, right? Medical system, light supporting system. Without digital design, the accuracy that we are providing to measure anything, if you want to diagnose any disease, we have a digital design that will help the doctors and cure early. Automobile, tremendous. Now each and every car is coming with the different chips, right? Now if you see the modern cars, which has a more than 50 microcontroller chips. In one car, there is more than 50 microcontroller. It may be a cruise control, it may be a driverless car, it may be a driverless trains, your anti-lock brakes, which is again designed by the digital design, and it will help us. If the tire pressure goes low, it will indicate. If you meet with an accident, the airbag will open, right? All these things is thanks to the digital design. Avionics system, the flight simulator, right? The flight, right? And in the flight, they are moving on the pilot is putting on the driverless mode, and then it is safe because the digital design is working. If the pilot is not working, home appliances, you can name any appliances, washing machine, dishwasher, microwave oven, right? With all AI technology, it's coming. So digital design is part of our life. We cannot live without digital design. Right, so now let me go back to the main topic, right, which is our HDL is nothing but the hardware description language. So this description language will be used to model the digital design or design. So initially people started connecting discrete components such as, for example, transistors, capacitor, resistors on the PCB or on the board. But once the complexity is increased and repeatability required, right? When I say repeatability means we wanted to produce the chips in terms of lakhs, in terms of crores, right? At that time, if you start using the discrete manner, if you start using the manual, which is not possible, right? So when you wanted to achieve the more complexity, more repeatability, at that time you required a modeling concept. So that is nothing but the modeling concept of the hardware came in the picture around the 9060 or 9070. So you can model the hardware, right? How you can model the hardware? That can be done by describing the hardware by a common language. So as of now in the industry, there are mainly three language we are using to describe the hardware. And one of the language is called VHDL. So VHDL is nothing but so the full form of VHDL is very high speed integrated circuits hardware description language. So this is a VHDL language. VHDL is more popular in the Europe region, while not more popular into the, I would say, Asia or US region. Industries already started moving from the VHDL because of VHDL has some limitation. So to overcome the VHDL limitation, people have started using the Verilog, and there are some advantage. Verilog is easy to understand. It is more towards the what you are designing, right? The VHDL is more towards the English language, while Verilog is more towards the hardware modeling. And also the Verilog offer the capacity to handle the complex design, right? And that is the reason either in US or Asia, people have already moved to the Verilog. Even Europe is now started moving VHDL to Verilog as a modeling language. And whatever the IP they have designed into the VHDL, they have already started. So new IP definitely they are designing Verilog, but even the old legacy IP, which was already designed in VHDL since many years, they are now converting that VHDL to a Verilog, and they are verifying the conversion is correct, right? So now entire world is moving to the Verilog. So Verilog started way back in a 1984, and then major changes come in year 1995, which is called a Verilog 95. So if you have used the Verilog and Verilog compiler, you must have heard this Verilog 95. And then the another major change came in 2001, which is called a Verilog 01 or 2021. So by 2021, the size and complexity of the typical IC has evolved tremendously from 1980s. So enhancement happened in a Verilog in the year of 2011, then 12, and then the latest revolution also happened in Verilog in 2017. Right, so that is the reason you see the Verilog, which is called 2012, 1995, and all those stuff. And then the third language is called System Verilog. I also wanted to touch up over here in the last slides. What is the System Verilog? So it is basically, I would say, we will go into more detail, but as of now, I would say it is an extension of the Verilog IP or Verilog language. Okay, so what are the modeling levels, right? So there are different modeling levels available in the industry at a different, and each and every modeling level will offer a different level of granularity, right? So first modeling level, I would say, let me see, where is my mouse? And yeah, so the first modeling levels will be available, or the type of modeling is called a behavior modeling. So behavior modeling is nothing but very close to the specifications, right? So marketing team will research what is a market requirement, and based on the market requirement, they will prepare the spec. And at very, very high level, if you want to code the behavior level, right? Behavior level language, the behavior of that particular product that you can write into the abstract level, right? So abstract is nothing but the information is very, very high level. There is no detailed information available. So for example, if I take a one of the case, I wanted to manufacture a calculator, and that calculator do a simple work. It will do addition, subtraction, multiplication, and division. So this is my requirement. There will be a one chip that will do a 4 functionality. So if I wanted to model, okay, if I do a plus b, and my answer should be a plus b or a minus b, or a divided by b or a multiplied by b. So this is very, very high level. So that behavior I can capture as an abstract level, which is called a behavior modeling, right? Which is not a detail. If I go one more level detail, which is called a RTL. RTL stands for the register transfer level, right? So it is also told, or the other name of the RTL is also told a data flow. Why it is called a data flow is that means we are converting the high level spec, the high level abstract model into the registers. Register is nothing but your flip-flop. So once you are convert into flip-flop, and then when two flip-flop are talking, there is a combo logic between those two flip-flops. So what flip-flop will do? One flip-flop will transfer the data to the next flip-flop. In between, there is a processing unit. It may be your combo logic, it may be your memory, it may be your any bus protocol, it can be any logic. So that is the reason the name is given register transfer level. So it is transferring the data from one flop to another flop, and that is the reason the another name of this RTL is also given a data flow, right? So the data is flowing. What is the difference between the behavior and RTL? RTL has a much more detail. RTL has a also the timing detail. That means RTL will tell you at each and every clock cycle what is the things which is going to happen. Right here, I am capturing only the very basic functionality. I want a calculator which has a 2 inputs and it has a 4 function. That's it. But I don't know that calculator will operate on 1 gigahertz, whether the calculator will operate on 10 gigahertz. That means if I wanted to multiply 2 raised to 10 multiply by, let us say, 5 raised to 10, the answer will come in 1 millisecond or 1 nanosecond, right? So that timing information is not there. The timing information will capture over here, right? So that is a RTL along with the functionality. So which is called a RTL abstract modeling. If you go to one level down, right? So that which is called a gate level. What is the gate level? It is also called a structure level. So it will not only capture the functionality, but it will also capture the structure. What is the meaning of structure? That means I'm converting my RTL into the gate. What are the gate? AND gate, OR gate, exclusive OR gate, multiplexer, flip-flop, you name any gate, right? So that means you are converting your register transfer level or RTL language into the gate level. Again, this can be a Verilog, right? So again, most of the time it is a Verilog. So Verilog gate level will be convert your functionality into the gates. What is the information this has apart from the RTL? RTL doesn't have, if I wanted to create a calculator chip, I don't know, my chip will be 5 by 5 mm square or 2 by 2 mm square. What is the area? I don't know, right? I know only the speed, I know the performance, but I don't know the area. So the area, the extra information will be added on top of the functionality, right? Which is not only the structure, but the area. Also, it will add the power. When I do any processing, when I do multiply, when I do division, how much power it will use. So those granularity, the area, the power, everything will be captured over here on top of the what is captured in RTL. And the next level you go, which is called a digital switch level. When I say switch level, it is nothing but it may be your transistors, it may be your CMOS resistors, capacitor, right? So you are going very close to the actual electronics component. So this is the actual or very close to the silicon, which chip is going to come out from the manufacture unit, while this behavior is very close to the spec. So these are the different level of the hardware modeling generally we are seeing. Okay, let me know if you have any doubt. You can interrupt me and we can discuss. So this is a typical ASIC flow. So what will happen in a typical ASIC flow is, as I told, there is a marketing team. Marketing team will go to the market, will figure out the requirement, and that requirement will be given to the architecture team. So architecture team will write some specification. So that specification will have a very high level details, what product we wanted to build, and that high level things will be captured either into the PDF or documentation, or it may be some modeling, MATLAB modeling and anything, right? And then they will figure out whether this product is possible or not, whatever the marketing team has come up with those inputs, and can we able to make this product, can it be realized, right, with limited of the power, with limited of the area, and with the limited of the cost, right? So everything they will check, we can check, and after that, that spec or information will pass to the another team, which is called RTL modeling team. So RTL modeling team will take those specification and convert those document into the RTL, right? So register transfer level language, where it has a clock information, it has a reset information, it has all the functionality will be captured. So again, RTL team will do the modeling either in a Verilog or Vhdl, or maybe a system Verilog, right? So these are the three different languages the team will use, and then it will try to capture all these details. Once the RTL is ready, right? So again, RTL is a continuous activity. It's not like that once you get the spec and within 1 month, 2 months, you are able to deliver the RTL, right? Which is continuous process. So what will happen? Once the RTL is ready, you will give this RTL to the two team. One team is called the synthesis team, and another team is called a verification team. So the RTL is given to the verification team. What the verification team will do? They will cross verify whatever you have written is exactly matching with the spec or not. So the verification team will also read the spec. They will come up with the test bench and specific test cases. They will run those test cases on top of the RTL model that you are providing. And they will do the simulation, and they will verify whether the intention is met as per the spec or not. That means if I wanted to implement A plus B, is it really A plus B, or it is A plus B plus A, right? So those kind of simulation will be done through some regression. So there are some test cases which will run on the RTL model, and same RTL will be also taken by the synthesis team. So what the synthesis team will do is it will again convert that RTL modeling into the gate level modeling. As we discussed, it will convert the RTL into the netlist. So netlist is nothing but the sea of gates: AND gate, OR gate, exclusive OR gate, buffer, inverter. So all this will be converted into the synthesis level. Once you convert the synthesis level, it may be possible during this conversion from RTL to synthesis, I have lost my functionality, right? Because of XYZ reason. So here my intention was A plus B, but when I convert into the gate level netlist, my functionality becomes A plus B plus A rather than simply A plus B. So what happened? There are some EDA tools available in the market. One is called the LEC, logical equivalence tool from the Cadence, and there is another tool called formality from the Synopsys. So this tool will help you to validate whatever the functionality you had coded in the RTL, which exactly matching when you convert from one modeling option to the another modeling option. So here we are making sure the functionality is intact, even the conversion happen after the gate level. So there are EDA tools are also available.
May I interrupt you?
Sure.
Yeah. So can you specify the reason that why during synthesis actually your functionality is going to be disturbed?
Right. Okay.
What are the
So
reasons?
there are a couple of reasons, right? So one thing is if your synthesis tool is not matured enough, and let us say you have some corner case, the way you written the RTL and synthesis tool did not understand that RTL is correct or not. Now take the example, let us say you wanted to model the flop in the design, but by mistake you model the latches, right, while writing the RTL. Your intention was a flop, but you model the latches. Or let us say during the RTL, you are another example is, let us say you are writing the RTL and there are thousand of pins, right? You are working with the in terms of millions pins, millions wire, and we are human. And while connecting, let us say I have not connected one wire, right? If I do not connect that wire, what will happen during the synthesis? That unconnected input becomes tied to 0 during the synthesis by the synthesis tool. When it is tied to 0, it will optimize my logic, depends on the logic 0. Ideally, I should try from the another IP, but I have not connected by mistake. I skipped it, right? It will be catched by simulation, but simulation will take some time, maybe 1 week, one month, 1 year, right? And by that time, let us say that logic 0 will optimize your, because of the logic 0 or tie 0, the logic got optimized, right? And then you will not match, because that whatever the logic is optimized, let us say it is optimized my A multiplied by B logic. So my multiplication is not correct, right? This is second thing. Third thing is we are also inserting the scan chain, right? So scan chain is nothing but there is a one domain which is called DFT, design for taste. So when the silicon is available, you wanted to taste the design, right? You wanted to debug the design. If there is any problem in the silicon, you wanted to debug. You wanted to get certain FSM or finite state machine registers output at the pin level, and you wanted to debug whether what is the problem, right? So we are also adding some DFT logic during the synthesis. So we are purposefully adding some logic which is not useful to the customer, but it is useful only for the ourselves. So let us say when Intel is building the logic, Intel is adding the two part which is called DFT, design for taste, and they are also adding design for debug, which is called DFD. So apart from my addition, multiplication, subtraction, or division, I am going adding one more logic which is not interest for the customer. It will consume the area, power, but it will help me to debug if my silicon will not work. So I am manipulating some logic, right? And because of that, I wanted to make sure my original functionality is intact. And that is the reason I wanted to do this functional verification. And that is the reason where when I'm adding something else, I may interrupt the original functionality, right? So there are a couple of reasons we have to do the equivalence checks or equivalence verification. Does it answer a question, or you have some
No,
more
got it,
doubts?
got it. 100% got it.
Okay, good. So this is called a front end, right? So whatever the spec, RTL, then simulation, then you do a synthesis, and then you cross verify the gate level netlist is equivalent. And then the data will be given to the backend. So what backend will do is they will take over the netlist over here. And then by taking the netlist, as they will do a scan chain, they will also create the clock tree. What is the clock tree? So at RTL level, I have, let us say, in my design are 2 clocks, right? Or 10 clocks, for example. So 10 clocks I have, and then I will connect those 10 clocks to each and every flop. I'm done. But when they place the gates into a different chip physical location, right? So let us say my IC is at 10 mm square. So one register is sitting into the one corner and other flop is sitting into the another corner, and both flop are talking to each other, for example. At that time, you need to make sure the clock reaching to both flop is more or less balanced, right? And because of the balancing, they have to do the clock tree insertion. So that is nothing but they are balancing the clock between all the flop those flop which are talking immediately, right? Which is called a clock tree balancing. So they do a clock tree balancing, and they will also place it. So as I told, one flop is sitting on left side corner, one flop is sitting on right side corner, my CPU is sitting somewhere else, my memory is sitting somewhere else, my DDR is sitting somewhere else, my USB IP is sitting somewhere else, right? So depending upon the placement, they have to make sure the placement is done and the routing is also done. So placement and routing is done, and then they will do, the backend team will do the DRC. DRC is called design rule check. What they will do is, let us say I'm building the chip in a 5 nanometer. So after building this chip, I am going to give this chip to the manufacture unit or the foundry, which is going to manufacture this particular chip. So they have a certain rules. They have a certain parameter. So we need to make sure that parameter is also met, right? So there are design rule check performance done by the backend team. So which is called a DRC. And then after the placement and route, right? Maybe because of that placement, your chip is bigger in size and you have a lot of CPU, you have a lot of memory. And because of that, now you will not meet the timing. As I told, one flop is sitting somewhere else, one flop is sitting to the extremely corner, and both are talking, and you have no idea, and you do not have a space to create both flop together, right? All right. So at the time, your routing is also complicated. So then the other challenge the backend team will face is about the meeting the timing. That means if both flop are talking to each other, and we have to meet timing in a default cycle. When I say default cycle, means my setup timing is one clock cycle, right? So I have to meet my setup and hold in a one clock cycle, which is my default timing. So that is called static timing analysis. So I will analyze whether I'm meeting my timing for each and every flops. We are not talking about 1, 2, 10, 15, 100 flops. We are talking about 20 billions flops. So you can imagine the complexity that backend team handle at the placement and route. Here we are talking about billions wires, billions routing wires, and billions of flops. So we need to make sure the timing analysis also met between those flops, billions flops, right? So this is all challenge for the physical design team, and they will not easily meet the setup time, hold time, and then again to meet the setup and hold time, they will introduce the inverter and buffer into the design. So again, they are ideally not changing the functionality, but they are changing the gates. So once they change the gate, they will dump the netlist, and that netlist FEV I will do with my RTL. So again, one more verification will happen, which is called equivalence checks verification, whatever Mitesh asked, right? So same thing over here, we will repeat that by doing all this stuff, right? I have not altered my basic functionality. So again, the LEC, logical equivalence checks, will be happen between RTL and netlist. And once you are ready with the data, once you have a full confidence, I have not hamper my functionality. My timing is made, my placement and routing looks good, my DRC is green signal, my clock doesn't have any skew problem. Then you are ready to do a tape out, or sometimes it is also called tape in, or sometimes it is called PG. PG means pattern generation. So that means we are ready to send this GDS database to the foundry. So GDS is nothing but one type of binary database which has all the information which foundry require to manufacture the silicon. So we have a foundry in Taiwan, then US, Singapore, right? So a lot of places we have a foundry, and that foundry we will send, and that foundry will manufacture your silicon depends on the technology, whether it is 7 nanometer, 5 nanometer, 3 nanometer, they will build, and then chip will be come out from the foundry. So this is typical the ASIC flow. Okay, if no other question, then I can go to the next slide. Okay, so RTL modeling, right? So let's talk about the RTL modeling. So RTL modeling structure, either it can be Verilog or system Verilog. So this is how it looks like. So we will define a word which is called a module, and then we will give one name, right? So this name will tell you a superficial functionality of that particular block. So you can give it any name. You can give module space my module, or you can give a add bit, right? So you can give any name. So module is a keyword, and then you will define, let us say, in that my module, how many input and output you have. So for example, in this, we have a and B, which is an input. We have a CI, which is also an input, and we have a two output, which is called sum. And let us say CO means maybe carry, or carry output, or output, right? Any name you can give. Now, this input and output, it may be a single bit, or sometimes it may be a multi-bit, right? So this is called a port declaration. That means I have a one module, and which module has it this many ports, this many interface, this many pins, or this many boundary, or this many lakes, right? Now that lake can be a single vector, it can be a multiple vector. So if it is a multiple vector, you can use one of the a keyword in the Verilog and system Verilog, which is called a parameter. And let us see, if I define n equal to 8, that means my this input A and B is n minus 1 down to 0. That means 7 down to 0. So we'll start from 0 to 7. So basically it is 8-bit. So my A and B is a 8-bit input. My CI is a single bit because I have not defined anything over here, right? So A, B, and C, or CI, I have a 3 input, while A, B is a 8-bit, C is a single bit. And I have a sum. So sum is also a 8-bit or 7 down to 0. And then I have another output, which is C0, which is a single bit. And then you will define the functionality in terms of clock over here, right? So that whatever functionality you wanted to code, you will code over here. So this is how the RTL modeling, if you want to model in Verilog or system Verilog, it looks like. So this is very, very high level. Okay, so I think this is a 2 example I have taken how it looks like rather than just a template. So previous one was template, and here I have mentioned this is how it looks like, right? So this is one of the things over where we have defined a module RTL adder. So let us say this is my one of the simple module which will do the addition, right? Let us say if we take the same example of calculator, I wanted to add one module which is do addition. So I can define I have a 3 input A, B, C, and then I have a 2 output sum and C0, and then I will assign my C0 comma sum equal to A plus B plus C. So what will happen is whatever input A, B, and C, right? C is nothing but the carry input, right? So if there is any carry which is available from the previous addition, that way you can also add over here. Now this C0 and sum is nothing but my output, and this output is the way. So when you define this output in this bracket, it will act as a concatenate. So that means my sum. So sum is also 1 bit, CO is also a 1 bit, right? So when I add all this A plus B plus C, so whatever my LSB will go to sum, and the MSB will go to C0. This is how it will be assigned, and that output will be available at your output boundary. Same way, let us say I wanted to define adder and subtractor both, right? Here I have defined only just adder. If I wanted to define adder and subtractor, now this is very, very simple logic, but here I have added one more extra, which is called clock. Here you see this is simple addition. I haven't used any clock, but here I have added the clock. Why the clock is required in a simple addition and subtraction? Let us say you wanted to use a multiple addition, right? Here we are not talking about the single bit. Here we are talking about the multi-bit addition. And that addition you wanted to store somewhere, and after storing, you wanted to use that stored output to process some things, to decide something, right? If my output is more than 100, do something. If my output is less than 50, do something, right? So those kind of specification is there, or those kind of requirement is there. You have to store your output, because you require to compare it, whether my output is more than 100, then take this decision. If my output is less than 50, then take this decision. So you have to store that output. When you store that output, you require a flip-flop, because flip-flop is nothing but a storing element. When you add the flip-flop in your design, you require a clock, right? And that is the reason this clock got added. So what we are doing over here, this is a simple mechanism. I can either add or either I can subtract. Depends on one of my input, which is called mode. So this mode bit will tell me whether I am in a adder mode or whether I am in a subtractor mode. So this is how it is written. So when the flops comes, we will always use the always keyword, which is nothing but the Verilog keyword.
So, Keyur, what
Yeah,
exactly we are doing at our end, whenever we will have to store the output, we will declare the output as a range.
that's
So,
right.
it is a similar thing what you have discussed.
Yes,
Okay.
this is a similar thing. You're correct,
Okay.
right? So when I say range, that means nothing but the registers or flops, right? And when I wanted to code the registers, I will use a keyword which is called always underscore ff. So that means I wanted that synthesis tool will create a flip flop. So always underscore ff at the rate. Again, this is all keyword. then bracket, and then you will write pause age, and then you will define one more variable. 99% it is a clock. So what you will tell, hey, whatever the variable is defined at the age of the positive edge, that means clock is toggling. So you are going to toggle the clock from your test bench, right? So test bench has a three. So we have a 3 input and 1 output. So these 3 inputs will be driven from the test bench, and one of the input is clock. So clock will be toggled from the test bench. So as soon as the clock will toggle, and when the positive edge comes, the execution of the next lines will happen. If the clock is not toggle, nothing will happen. It will directly go to the end module, right? So that means when the clock is toggle and when the positive edge comes, do something. What is the something? The next line. The next line is telling, if my mode is 0, do the addition. If my mode is 0, else, then do the subtraction. So this is what we are doing. So I am taking the 32-bit A, 32-bit B, and I am doing addition, and I am giving those the result into the sum, which is nothing but my, again, a 32-bit sum, 31 down to 0. If my mode bit is 0, again this mode bit you can control from the test bench. So if the my mode bit is 1, I will do subtraction, and I am putting into the sum. So I wanted to store this sum because I wanted to give to the test bench back to verify whatever the addition and subtraction I'm doing is correct or not, right? And that is the reason we can define output range sum. Instead of logic, you can also define range over here. Whatever Dr. Mitesh told, output range and sum. So you wanted to store this sum, and after storing, you wanted to give back to the test bench. So test bench will make sure whatever A and B, and depends on the mode whether the result is correct or not. So they will validate it, and that is the reason you require a always kind of keyword while you coding the RTL. Okay, so here you see the difference. Here I have used the equal sign, right? And here I have used less than equal, right? So what is the difference between equal sign and less than equal, right? So which is described over here. So if you use equal sign, which is called a blocking assignment, and if you use less than equal sign, which is called a non-blocking assignment, right? So this is a very good concept in a Verilog. And generally, if you go for the job and people are asking, this is a favorite interview question. Each and everybody is asking, what is the difference between blocking and non-blocking a statement in Verilog, and in which case you will use blocking, which case you will use a non-blocking, right? So this is a very good concept. So what will happen, let us say when you use equal rather than less than equal, that means you are using blocking assignment, right? And this is nothing but when you use has tan. So tan is nothing but the time delay. So that means I'm assigning something to A, but after 10 unit time. That unit time, it may be picosecond, nanosecond, microsecond, depends on your simulation time. So I am assigning something to A. What I am assigning is I am assigning one tick B1. So that means logic 1 I am assigning to A. But when after 10 unit time, right? So the simulator will assign one tick B1 to the A after 10. Now what is my next line? Next line is assign B to 0. One tick B0, logic 0 is assigned to B. But we have written has 20. And here I have used an equal sign. That means this is blocking statement. Blocking means this second line will not executed till the first line will execute. So when the first line is completed, then and then it will execute the second line till it will block. Till the second line will not completed, third line will not execute till it will block. That is called blocking statement. So that means the assignment of the logic 1 will go to the A after 10 unit time. Assignment of 0 will go to the B after 10 plus 20. So that means 30 time, 30 unit time, not on 20. And the assignment of C will happen, which is one tick B1 will happen to the C after 10 plus 20 plus 40. So when you release your reset and when you start the execution, the third line will execute after 70 timestamp. It may be nanosecond, 70 nanosecond, picosecond. Again, it based on the on which technology, on which frequency you are operating, right? So This is the difference between blocking. So that means it will execute in a sequence manner. It will not execute in a parallel fashion. So this will create a combinational logic one by one. So one output will wait for another output will go to the third, and it will wait till second output is not stable, right? So this way. If it is non-blocking, what will happen is you will use less than equal. So same here, ABC, we have used DEF. So same logic. So one tick B1 will be assigned to D as soon as the 10 time period is done. One tick B0 will be assigned to E as soon as the 20 time period is done. We are not waiting 20 plus 10, 30, right? And then F will be assigned one tick B1 to S after 14 nanoseconds. We are not waiting 10 plus 20 plus 40. Let us say this 10, 20 is not there. I am assigning directly D equal to one tick B1 equal to one tick B0, F equal to one tick B1. In all scenario, this value will be assigned on the same clock cycle to DEF. They will not wait when my first, second, and third will finished, and then I will do. So this is called a parallel execution. So if you see the electronic circuit, the current will go in each and every branch. Current is not waiting, let me go in first branch, then second branch, and third branch, right? Current is go as soon as you start your power supply, it will go in each and every branch, right? Which is a parallel execution, right? So non-blocking assignment is used when you wanted to do the parallel simulation. Another thing, very interesting, right? This is again interview question. Many companies are asking blocking and non-blocking statement, right? So for example, I wanted to create a shift registers, right? So shift register is nothing but the output of the first flop will go to the input to the second, and output of the second will go to the third, fourth, fifth, right? What I will do is, I know the registers. As soon as the registers I wanted to form, I have to use the clock, right? So I will use this clock, right? Let us say, and I'm going to use this always block, correct? So I'll always, again a keyword, then at the rate, then I will use the posage, and then clock, and then bracket complete. So what will happen? Okay, so before we go to the detail, what all input we have? We have a input A, we have a input clock, and then we have a output C. Okay, so this is nothing but the simple flop I wanted to create. What I'm doing is, at the every positive edge of the clock, I wanted to assign A to B, and then B is assigned to C. But if I use the equal sign rather than less than equal, if I use the blocking assignment, what will happen? At the positive edge of the clock, A will assign to B, and because of the clock, the synthesis tool will take this line and will create the flop like this. So this is A input, and the output Q becomes my B. You see, this is a B. And then B I am assigning to C, correct? So as soon as this statement complete, I wanted to assign. So B and C will be same. Okay, so this blocking statement is nothing but used for the combinational logic. So this is a combinational logic with the buffer, right? There is no logic, but it is buffer, I would say. So between B and C, it is a buffer, right? So this is a combinational logic. While non-blocking, how it will affect? Again, same input clock A and output C. So what happen is, instead of just equal, use less than equal. So A will be assigned to B. Because of this always block and posage, it will create the flop, and this B is becomes, and then B is again non-blocked by C. Okay, so that means you assume this statement was not there. So that means always a positive edge clock, and then directly B to C, right? Because everything is concurrent, everything is parallel, right? So in parallel simulation, what happened? This A equal to B is true for the positive edge, and B is assigned to C is also true for the positive edge. But here it is not there. Here what happened? When B is finished, then it is applicable. At the time, this clock is gone. Correct. Here, when B is assigned to C, there is a clock. So this always come in picture while this C less than equal to B or second line will executed. When second line is executed, clock was there. So it will map register like this. Right. So this is also a pitfall. Sometimes what happen? I wanted to create a SIP registers. I wanted to create a back-to-back registers. But if I make a mistake, instead of less than equal, if I directly use equal, I will end up with the single flop rather than two flops, right? So these are also a pitfall, or I would say we have to understand the difference between blocking and non-blocking.
So one participant has put one question in the chat window.
Okay.
Difference between concurrent and parallel.
Okay. So parallel means everything. So whatever is we are telling, right? Non-blocking, everything will be a parallel. Concurrent means, I think in English point of view, concurrent means it will do a one by one, right? For example, your C language, right? C language is one by one. So when you execute first, then it will go to second, then it will go to third, then it will go to the fourth, right? So if it is a sequence one by one, which is called the other way, which is not a parallel.
One participant has raised the hand. I think she is Monica. Yeah. Do you want to ask any question, Monica,
Yes,
madam?
sir.
Yeah, please.
Good afternoon, sir. Sir, in the first block, you said that both B and C will have the same value, but these value will be updated at different times, right?
Are you talking about this block?
Yeah, first block.
Right.
So how will you, how the values will be updated at the same time? Will you use a buffer or something like that to update the value?
Right. So
Because
this is
B
a
will get the
Mhm.
value early and
Yes. So A will, okay. So here what happened, positive edge of the clock, A will be assigned to B. Okay. A will be assigned to B. So the register will be put by the synthesis tool. Now what happened, the same B, right, will be assigned to C. So when this statement is executed with the help of the clock, then it will go to the next statement. So next statement also I'm telling B and C are equal. But here I have not used the less than equal. So what will happen is B and C will be equal with, so it is the same wire, or I would say buffer, right? Buffer is equivalent to wire, right? So this B and C will be same. So first B equal to A will be executed, and after, once you know the value of B, right? Assume, let us say A is 5, and when the clock, positive edge of the clock will come, this A will transfer to the B. So B is also become 5. Once the transformation is done, then you are assigning B to C. So that means if B is 5, C is also 5. So that means B and C is nothing but the single wire. So here also some consumer will be there. Here also some consumer will be there. Okay. So both are equal.
So exactly what you want to say, that second statement has missed the clock, right? That's why over there the buffer is created,
Correct. Or second statement, it may be possible like this, correct?
right?
Second statement is like this. I want only single flop, right? So I have coded like this. And then I wanted to assign B to C, but I wanted to assign C equal to inverted, okay, exclamatory sign. C equal to exclamatory sign and then B, right? Do we have a white space where I can write? Or
Uh, Maybe whiteboard is available.
yeah, whiteboard.
The option nearest to that, leave the meeting.
Right, right.
On top of it, you are getting the
Yeah,
white.
I got it. Right, let me open. Okay, so now you assume I wanted to, okay, let it come, I think. Can you able to see this whiteboard?
yes, sir.
Yeah.
Okay, so 1 minute. Okay, I was going back to the main window. Okay, so what happened? Okay, allow me to write here, pen. No, this is laser, this is pen. Okay, I can write like this. Okay, so let us say I have written my B equal to, sorry, A. Okay, and then I am writing C equal to This is exclamatory sign, and then I'm writing B. So that means I'm inverting my B by sending to C. If I write like this, what will happen? There is one inverter come over here, and the C will be after the inversion of B. If this is a case, and I wanted just B like this, and C will be like this, right? Then I can also use this kind of thing. Make sense?
Yes, sir.
Or I
Yes.
confuse more? Okay, so the bottom line is, again, this will execute one by one in a sequence. So first A will be assigned to B when there is a positive edge. So if the A value is, let us say, 1 tick B1, okay, because this is a digital, so let's talk about 0 and 1 rather than the decimal 5 we talk, right? So let us say A is 1 tick B1. So A will be go to B. So this A will be go to Q output when there is a positive edge. And let us say A was 1, so B becomes 1. Now, after that time, when this is executed, at the time this clock is gone, correct? Because C equal to B, the second line is waited till this finish. And when this finish, when the clock comes. And when the clock is gone, this is also gone, this is also gone. So there is only a simple statement, B equal to C. So that's why there is no flop added, and B and C become same.
Sir, so that means there will be some time lag between the time at which B and C will get updated.
Yes, but here there is no time limit, right? If you see the previous one, if you
Yes.
put this kind of time, then yes, it is possible. Okay, so that means here I am also updating my B, but after 20 unit time, or C I am updating after 40. So then time will be there, but here there is no time, right? Here I have not put has. So there is no time. Okay, so that's why B and C becomes same. So now there is one branch and some flop will be connected over. There is another branch, some flop will be connected over here. But in this case, what happened? Positive edge clock. As soon as clock comes, this statement will be also executed and this statement will be also executed. So you assume it is written always pause edge clock, B less than equal to A, and then there is another positive edge clock and written C less than equal to B. Right? So you have to assume like this because this is a parallel process. So in this parallel process, the pause edge of clock will be stick to first line and it will be also stick to the second line as well. And that's why the synthesis tool will create the flop. Okay, two flop. Make sense? Because both are same. So when A is assigned to B and B is assigned to C, at that time clock is there. So that's why the same clock is going to the both when B is also assigned to C. So in this case, what happened? Let us say, assume A, B, C all are 0. Same case. Now A becomes 1 tick B1. So this logic 1 will be transferred to over here in this clock. At the same clock, what was the B? B was 0. So 0 was transferred to C. So in this case, at the end of one clock cycle, this B and C becomes 1 tick B1. But in this case, after one clock cycle, my B is 1, but C is still 0. Why C is still 0? Because C took the clock of the previous B. And what was the B? B previously was 0. Before the first clock cycle came, the B was 0. So that 0 was transferred over here, and then 1 was transferred over here. So B becomes 1, but C becomes 0. So there is a difference. If my A is 1, in this case, both are 0. And here B is 1, but C is still 0. In this case, B and C both are 1. Understood? Because same clock is coming, right? So as soon as the clock comes, A will transfer to B. And as soon as this clock comes, B will transfer to the C. And both happen at same time. Yeah, I think you have question more. Go ahead.
Yes, sir. Sir, can we infer that the number of flip-flops after synthesis will be always be equal to the number of statements in the non-blocking procedure?
More or less, yes.
Can we
But
infer
let
it
us
like
say,
that?
more or less, yes. But let us say if you have a bits like this, right? A multi bits, for example. Here you see, where is my mouse? Yeah, here if you see, right, this sum is also my registers, right? Sum is also my flip-flop. But what is a flip-flop? It is 32. But I have written always block only one time. I have not written 32 times. But here
Okay.
the
Okay,
sum will
got
be
it, sir.
32 bits, right? 32-bit vector. So yes, I mean in very simple term, I would say yes, but not like that. It depends on the number of bits. Okay, I think if I take the previous question, right? So
Okay,
I
thank you, sir.
think, yeah, welcome. Concurrent and what was the question? Concurrent,
Parallel.
if parallel.
Parallel. Yeah.
I think concurrent and parallel, right? Concurrent is also one kind of a parallel, right? It is
Yeah.
not a sequence, correct?
Yeah. It is parallel.
It is a parallel, right? So both are same, right? So which is nothing but my non-blocking statement only,
Yeah.
right? Concurrent and parallel, both are same, no difference. I think I missed. Generally, we use a parallel rather than concurrent, so I missed it. So both are same. So my non-blocking statement is nothing but the concurrent statement, and my blocking is a sequential statement. It is just like C. When C complete one thing, then it will go to the next statement, and next statement complete, it will go to the third statement, right? But the current and the voltage will go simultaneously in all branches, right? So that is the difference between C language and Verilog language. Verilog language is more close to the hardware behavior, while C is nothing but the logic language, right? Depends on one output, you will decide something, what to do, and it will go in one by one. Okay, makes sense? Or if there is any few more questions, I can take up.
Yeah. Any questions from participants? Please, I request all of you to make the session interactive. Okay. So I think there is no question. So I am having one question that while writing the stimulus for the given DUT, we are normally using the blocking statement because we will have to pass the I can say the test case one by one.
That's right.
Am I right? So while writing the stimulus, we are normally preferring the blocking statement
Blocking statement, yes.
instead of non-blocking. Okay.
The reason is also you are driving something. Look at,
Yeah.
you are not registering something, right?
Right.
When you do non-blocking, you wanted to registers. You wanted to create a flops. You wanted to register some value. If you want to registers, then and then you should use the non-blocking. But in test bench, what is the test bench? We are driving the inputs.
Right.
And we are consuming the output. So whatever output comes from that particular block, we are consuming in a test bench, and whatever input to the block, we will drive those values, right? And that is the reason we do not require to latch it. We do not require to register it. We do not require to store it. And that is the reason you can use equal sign.
Right.
Okay. Okay, so this is another, I think, interesting. I don't know, you people know, don't know, right? So this is again very simple. And a lot of company, if you go for the interview, people will ask this question, right? How you can model the asynchronous flop in a Verilog, and how you can model the synchronous flop in the Verilog, right? So the difference between asynchronous flop and synchronous flop is depends on the way the reset is connected. So for example, looks like my mouse is stuck. Yeah. Okay, now I got it. So okay, so if you see a flop has, let us say, the D input, flop has a clock input, and flop has a Q output. On top of that, many flop has a reset input as well, right? If it is active low, the bubble will be there, and let us say this is the pin is called RSTN. RST means reset, and means negative, active, low, which is called N. So that means it is active low. So that means when you apply logic 0, the Q will be resetted, right? So that's why it is RSTN. Now, this is called asynchronous flop. That means irrespective of your data, irrespective of the clock condition, when you apply reset, Q will go to the 0, which is called async flop. If I wanted to model async flop, what you will do is you will define D reset clock as an input, and you will define Q as a output, right? This is my output. And then you will write a keyword which is called always at the rate or at pause edge of the clock. So that means I'm waiting when my clock will becomes positive. Or if the clock is not positive, don't worry. If the negative of the reset is come because of this bubble, I'm using nag edge rather than pause edge. I'm using nag edge because of this bubble. So I'm using or nag edge of the RSTN. Then do something, begin, and then this is end. Okay, so this begin as a this end. Do something. If anything happen, whether my clock becomes positive or my reset becomes negative, that means apply 0. Do something. What you want to do? Then if my reset is 0, the Q will be 0. Else D will be propagate to Q. That means this input will go to the output like this. That means when the reset is not applied, right? Only this clock come, then make your Q equal to D or D equal to Q. I mean, D value will be reflected at the Q. When the reset is not applied, but when the clock is come. So that means either in one condition, either clock go high or either reset go high. Either in one condition, you will go to this line until unless you will not go to line. So that means even though you are not applying any reset, even though you are not applying any clock, at that time nothing will be executed. It will directly go to end module. In that case, what happen? Whatever the Q value from the previous cycle will retain that value. That's it. So that is the reason it is called flop. That will retain the logic when there is no change in the clock age and no change in D and no change in reset if it is asynchronous. Right? So this is very simple, I think. Now, if it is a synchronous flop, what is the meaning of synchronous flop? That means if I go to the previous slide, which is asynchronous, synchronous means if my clock is not active and if I apply reset, it discard, it will not reset. Okay, that is called synchronous. So that means my reset will be also active at that time my clock is active. You got it? What I'm telling? Okay, so when the clock is positive age, at that time, if my reset is 0, then my Q will be reset. Otherwise, Q will be not reset and it will be ignored, which is called a sync flop. So it doesn't have a look at this flop. How many inputs and how many outputs? Just 2 input. One is data, one is clock, and one output Q. In previous case, it has a data, clock, reset, and Q. So now reset is not part of my sync flop. The reset is part of your data logic. You see, that is a difference. Okay, so that means if my clock is not active and if somebody apply reset, don't reset my Q. I wanted to ignore it. I wanted to take the changes when my clock is active. How I can model? Same RTL, nothing, only just one line change I will do. Always clock, pause edge of clock. I have not written or. You see the difference. This line I have discarded. Okay, if it is async. What I will do, I will always check when my clock is active, when it go from high to low. That means this case, right? This case. When it is go from low to high because it is pause age, then I will do something. Otherwise, I will not do anything. I will directly go to end module. So if my clock is active, I will check it. When my clock is active, whether my reset is also 0. If reset is 0, make it 0. But when my clock is active and if reset is not 0, directly jump over here else statement. Then I will transfer my input to output. So D will go to the Q.
So alternatively, can we able to say like this, that in the previous example, reset is acting as a level trigger signal, while in the next example, the reset is acting as a edge trigger signal?
Reset is acting as a, so
Level
reset is here acting synchronously, right?
With reference to edge of the clock.
Correct. So when the clock comes and at the time if the reset is also asserted,
Yeah,
then it will make an effect, right? So when the clock comes 0 to 1, which is a very, very small window, very, very tiny window, right? And during that time, the reset should be also active. So again, I go back to your questions. You are telling in previous example, the reset is acting as a
level trigger.
Level trigger. You are right, because as soon as the reset come, irrespective of condition of clock and D, it will be reset my queue.
Yes.
Right. So it is acting as a level trigger kind of thing. Here it is acting as a age trigger. And what is that age trigger? When the clock edge has come, at that time reset has to active. Then and then it will be reset. What is the advantage of this kind of design? If there is any glitch in the reset, in previous circuit, you are gone. All your data is lost because Q becomes 0. Let us say you have coded some FSM and FSM in a 7th state, and some glitch comes here, or somebody put by mistake did a reset. Your Q becomes 0, irrespective you are in a 7th state or 6th state or state number 0 or FSM state. Okay. So glitch can also affect your output. It may be a noise. When I say glitch, it can be a noise, right? But let us say in this case, what happened? If the clock, because clock will be active for a small period of time, very tiny time. At that time, if glitch comes, then and then it will be affect our output. And the chances are very, very less. That clock is also active, and at the time also glitch will come or noise will come, right? So that's why generally in industry, we prefer the synchronous reset flop to avoid the noise, to avoid the unnecessary reset, to avoid the glitches. But not always. Again, the design is mixed, but 70-80% it is a synchronous flop. This is way we code the RTL, and in some cases when we require a async reset, we can code the RTL in previous fashion. Only we need to change this assignment or. So depending either this condition is true or this condition is true, depends upon that it will go over here and check. But in this condition, it will only check based on the clock. If the clock is high, then and then it will check reset. Otherwise, no need to check. Even though reset becomes active, don't apply reset. Okay. Okay. So other thing is, I think case statement, right? You might be aware, we can also use the case statement to form a multiplexer in a Verilog or system Verilog, right? So sometimes this is another pitfall. I would say that the fall in which people generally make mistakes. Now, what I have done is, let us say I have a one select line, right, which is a 2-bit select line. This 2-bit select line will define or decide my output Y. Whether my output Y becomes A or B or C depends on the select line value. So I am writing this RTL in a Verilog using the always keyword. I'm beginning and then I'm writing case. Case is also a keyword in Verilog. So case and then bracket you will write a select. So select line is nothing but the input. ABC is also a input. Output is Y. So that upper section I have not written, right? So I'm talking about the upper section. What is input output, right? I'm directly capture this scenario, right? So let us say when you write case and then select. So this select value is nothing but this select value. Okay, this is 2 bits. So this is 2 tick B, either 0, 0. So when select value is 0, 0, A will go to Y. If the select value is 0, 1, B will go to Y. If the select value is 1, 0, C will go to Y. But what will happen when select value is 1, 1? It's not written, correct? So the decision statement, if it is incomplete while you write the RTL, right, it may be possible you are missing something. Your intention was not to create a 3x1 multiplexer. Generally, we have a 4x1 multiplexer, correct? But you don't know what are the different state, and you miss one state, and this becomes 3x1 multiplexer. So when your select value becomes 1, 1, what happened to Y? Whether Y is A or B or C. If I write RTL like this, and if my select value is, let us say 1, 1, what will happen? Somebody reply undefined. Okay.
Y will hold the previous state.
That's right. Now, what is the previous state? It can be this line, it can be this line, it can be this line. Now consider, let us say, first I did a select line 0, 1. So that means it will take this case. So y equal to b. And let us assume b was 5. Okay. It should be 0 or 1, but I hypothetical. So b was 5. So y becomes 5. After that, if I make select equal to 1, 1, it will go from this line, this line, this line. Nothing is matched. It will go to end. That means my y is not changing. So y will becomes 5 only. It will remain 5. Then again, if I change my select line to 1, 1, still y equal to 5. Then again, I change my select line equal to 0, 0. Then let us say b was 10. So y becomes 10 instead of 5. Then again, if I select my select line equal to 1, 1, then what is y? 10, not 5, right? So it will be previous value. What previous value was defined? Consider the case. My first select line is itself is 1, 1. Then, so while coding, sometimes we are initializing the variable y, right? In Verilog, I don't have, I think, that slide, but there is an initial keyword, right? So above this particular logic, you can initialize all your output. So if you have initialized your all output, let us say with the 0, 0, 0 or 1, 1, 1 or 1 or 0 or whatever default value, then if my first selection is 1, 1, then y will be that initialization value. If I have not initialized, what will happen in silicon? In silicon, when you do or when you deassert the reset, at that time, inside the silicon, there is a MOSFET, and that MOSFET will pick up one noise. It will always pick up some noise. And depending upon that noise, either the MOSFET will attain logic 0 or logic 1. So sometimes it is 0, sometimes it is 1 if it is not defined. It is not constant. So today, if I turn on my chip and if I do a select equal to 1, 1, today I'm getting y equal to 0. Tomorrow, let us see, if I power off and again power on, I may get 1. So depends upon that power turn on time. What is the noise that that particular CMOS or the transistor is taking? Whether it is taking high noise or low noise, depends on logic 1 or 0, it becomes, if it is not defined. So this is all bad practice. We should define the select, right? We should define all the number of cases, or we should initialize all the output to the default value, right? So I can initialize my all output y. Let us say here initial, I will write initial initial y equal to 1 tick b 0, and then if I miss, I have no problem. Or in other word, you can do like this, right? So previous was only just case statement, CASE, but this is something new, which is called case Z statement or Z statement. So why we want to use this Z statement and how the case Z statement will helpful. Again, assume this select line. Now, in previous case, it was just 2 bits. So there is 4 possibility. Now assume it is 4 bit. How many possibility? 16. I am lazy. I don't want to write 16 times, correct? What I can do is, again, this is the advantage of Verilog, right? The advantage of Verilog, you can use case Z statement. Instead of writing 16 times, I would have written only 1, 2, 3, 4, 5 times. And I have covered all 16 possibility. What I have done, instead of writing 1001, I have written question mark, you see? So this question mark means it can be anything. So means my select line is a 4 bit, right? 0, 3 down to 0 means 4 bit. So this is LSB, this is another LSB, this is another LSB, and this is MSB. So MSB is 1, irrespective of this 3 LSB, any value. If MSB is 1, my value will be 3 in hexadecimal. Okay, the priority is nothing but the output. Okay, this is output, which is a 3 bit, for example. So my priority becomes 3. The priority output becomes 3 if my MSB is 1, irrespective of the LSB, last 3 digit LSB, last 3 LSB, because it is a question mark. If my MSB is 0 and the next MSB is 1, irrespective of lower 2 LSB, my priority becomes 2. If all are 0, 0, then it is 7, right? So this way you can define you can optimize the logic. It is more simple. It is user-friendly language. This Verilog is a user-friendly language. This is one of the example. And this way, with this 5 statement, 4 statement, 3 statement, or even 1 statement, you can cover all 16 possibility by writing this question mark. If you write a question mark, the compiler need to understand. And because of that, you need to write a Z. If you do not write Z and if you write question mark, I think it will give an error, because it will confuse whether it is a this case and it has to ignore, or it has a question mark, right? So case Z and then you can question mark. So the simulator will behave as per this particular input that you have given. Okay. How the synthesis will behave, how the logic will behave, how the gate level modeling will happen in this case. Simulation you understood, right? Same way, I think, nothing much difference. In gate level also, when it will optimize, when it will create the logic for the priority by using AND gate and OR gate, the synthesis simulation to create the gate level modeling, it will use the Karnaugh map, and where in Karnaugh map it will write X. You remember in Karnaugh map during our bachelor we were writing X. X is nothing but X can be 0 or 1, and depending upon that we were optimizing the logic. So this is, in other word, instead of question mark it is X. So it is more optimized logic, right? So it will optimize in much more better way rather than you have all 16 cases. So gate level is more optimized logic. So you can save more power and area. Okay, another generally again interview question and very interesting, right? So sometimes what happen when we use this always block, okay, and then ideally in bracket we have to write all the variable that we are going to use below the always block. Okay, so now assume I have a 4 input A, B, C, and D, and I have a enable pin, and I have a output Z. Enable is also input, A, B, C, D is also input, Z is my output. So depends on the enable, my Z will be A plus B, or depends on the enable value, my Z will be C plus D. So either doing addition of A plus B or C plus B if my enable is 1. If my enable is 1, A plus B equal to Z. Else if enable is 0, then addition of C and D of Z will becomes. Now here I have missed input D in a sensitivity list. This is called sensitivity list. Okay, A, B, C, enable, Z, right? Here how many variable I have used? I have used 1, 2, 3, 4, 5, and 6, right? But I have missed a D. So if I missed D in a sensitivity list, how the compiler will work? Compiler will do if, so how the compiler will work? So generally compiler will go in this particular logic when there is a change in A, B, C, enable, or Z. Okay. So if there is any change in A, B, C, Z, compiler will go. So Z can be a part of sensitivities as an output. No, you are right, Ankur. I think you are right. Z is a, by mistake I write. Okay, Z should not be there. Let me change my slide. I think. Yeah, it's a mistake from my side. Thanks for correcting. Z should not be part of my sensitivity list. Am I audible?
Yeah, you are audible.
Okay, fine.
And thanks, Ankur, for good presence of mind.
Yeah, very good. So how the compiler will work? Whatever the input is present in the sensitivity list, if the input is changed, then it will go inside this particular always block. Otherwise, it will not go. Same way, right? In previous example, as I told, if there is a change in clock, right here, then and then it will go. If there is no change in clock, it will not go, even though the reset is tied to 0 or active low, right? Same way here, only input will. So if I have missed D, and let us say D is changing, previous value D was 3, now 3 becomes 5, or 1 becomes 0, or 0 becomes 1. In that case, compiler will not go, and compiler will not calculate the new value of Z depends on enable. Okay, so your simulation will miss something because you have wrongly written the RTL. But what happened to synthesis? Synthesis is nothing but the gate level netlist. It will go to the silicon. What is going to the silicon? The gate level, right? What is come in a chip? The gate level. But synthesis is smart enough. Okay, synthesis will assume. Look at for synthesis, it's very simple. Synthesis will create a mux. Okay, enable it will tie to the select line, and Z will be A plus B, and it will create C plus D equal to Z if the select line is 0. Simple. So for the synthesis, if you miss any input in a sensitivity list, synthesis will create exactly same behavior, whether I write D or whether I miss A, B, C or enable. Doesn't make any difference for the synthesis, because synthesis will not work on the whether input change then and then I will go or not. Synthesis will work on this condition. If enable is there, then it will do Z equal to A plus B, otherwise C plus D. So your silicon will be correct. There is no bug in silicon, but emulation will find a bug and they will ask the RTL designer to change the code. In that case, if you do not change the code, then your simulation and synthesis is out of sync. Whatever you are verifying is not you are sending in a silicon. So both are out of sync. Okay. So ideally, we should not miss any sensitivity list. So in the EDA, there are some tools. If you miss something like that, they will catch. Okay, so there are some EDA tools. One of the famous EDA tool is called Spyglass. So Spyglass is the name of company. Before it was name of, and now it becomes a Synopsys. Synopsys by that product. So Spyglass is a product from the Synopsys company, and they have come up with the linting rule, which is called a linting. So that will check the quality of the RTL. So whatever RTL you have written, if you miss this kind of things, the Synopsys lint tool or this Spyglass lint tool will catch and it will throw the error. Okay, and then you can correct it.
So you mean to say that before compilation, editor itself capable enough to identify the error?
No, so that is a different tool, right? So once you compile and everything,
okay,
after compilation, before you send to the verification team and synthesis team, you have to qualify your RTL. So we are running a bunch of tool, and one of the tool is Spyglass, and that will catch the quality of RTL. So if you miss something like that, it will catch. Look at this is not a syntax error, right? Syntax error will be catched by the compilation, so you will not able to proceed. But this is not a syntax error, right? So this is like a user mistake can be avoided or can be okay, because ultimately silicon behavior is not changing, right? Only simulation behavior is changing.
right.
So that's why the compiler will not tell anything, or maybe it will give a warning. But when you run in a Spyglass lint tool, it will throw error and it will tell, hey, please correct it.
Okay.
So it is after compilation. Okay. Okay, so I have taken a few example like whatever we discussed, right, which is a pitfall and where you need to make sure, right. Then I wanted to also discuss about the system Verilog, right. So system Verilog, again, as I told, it is extension of the Verilog, and system Verilog language is a much more powerful language compared to Verilog. When you wanted to work in a complex design and you want a quick output, efficient output, error-prone output, it is preferred to use a system Verilog. And now most of the industry or most of the company, I would say, have moved from Verilog to system Verilog. So we are also using now system Verilog. We are not using Verilog now. So how the system Verilog is created? So system Verilog was created by taking the goodness of the all languages, whether it is a Verilog, whether it is a Superlog, VHDL, PSL, either C, C++, Vera. So all the goodness of this language is taken, and then system Verilog is created. And system Verilog started initially in 2009. And then people started replacing the Verilog, right? And we are now 2021. It is almost now almost 12 years, 11 years plus, and people have using the system Verilog more rather than Verilog. So what are the advantage or where it will make impact? So the main impact of the system Verilog is this particular 5. So one is when you design any IP or when you integrate any IP into the SoC, system on chip, it will be very useful. I have some example later on. Then if you want to write a test bench, it is more simply and user friendly language when you want to write a test bench in a system Verilog compared to the Verilog language. And also the assertion, not sure whether you people are aware or not, right? So assertion is also a things which will help you to find a bug early. Before the verification team catch your RTL bug, you can also place assertion as a part of your RTL code, and you can also get whether it is fail or positive. I have also example I will discuss after some time. And then direct programming interface, and then SV API. So again, application programming interface, this is also helpful. So I've taken 2 example, not all 5, 2 to 3 example, right? So how it will be helpful? If you see traditional Verilog has a strict and confusing rule. For example, if I want to write a Verilog, then I will write module chip and then input wire and then in output. Sometimes you will, instead of wire, you will also use range, as Dr. Mitesh told, right? When you want to do a registers or you want to create a flop, you will use a range keyword. Otherwise, you will use a WIRE wire keyword. All this keyword is necessary. So sometimes when you are writing the things, initially you thought my out one will be just simply wire. It is just combinational logic, and you will define as a wire, and then you end up using as a range, right? And when you use as a range and you have defined wire, right? Then again you will get a compilation error and bonding and all the stuff. So the advantage of the system Verilog is, if I go to the next slide, no need to define as a wire or range or something. If you define just logic, LOGI key, whether input or output, irrespective, whether you want to use as a registers, whether you want to use as a wire, whether you want to use as a combinational logic or sequential logic, doesn't make any difference. They are allowed. So it is more user friendly, and it makes our life easy to think about whether it is range or wire. So you just define as a logic, whether input or output, and this logic has a, out of these 4, either it can be 0, it can be 1, it can be X, or it can be Z gate. You know difference between X and Z?
So actually Z, that is a high impedance. So whenever we are modeling the tri-state buffer, for example, and if my
Right.
enable input is 0, there is open path between input and output. Normally we refer that as a Z.
Correct. Correct. So it is tri-state, or I would say floating, right? So floating is also used as a Z in simulation, and X is undefined. You don't know whether it is 0 or 1. So when there is a connection is not proper, or it is the input is unconnected, the simulation will propagate X. X is can be 1 and 0, right? So these are the difference. So it can be anything, right? So either 0, 1, X or Z. So this way it is very simple. These are the advantage, right? So for example, system Verilog language is more powerful in terms of construct, and it will offer a very easy connectivity compared to the Verilog. So I have a couple of example I will discuss in next slide. And it is also when you try to integrate IP at the SOC. For example, I am a part of the SOC team, and we are integrating more than 250 IP into the SOC. And each IP has a 400 pins, 500 pins. So you can imagine 500 pins multiplied by that many IP, 250 IP. Now, when you integrate, you can imagine the number of wires, number of pins, number of interface that you are dealing with. And if you multiply, that number will go in thousands or lakhs, right? And sometimes it's very difficult to do each and every connectivity of that pin in a right manner. So the system Verilog will allow us to create an interface. And once you create the interface, then it is your life becomes again a simple. I will discuss in next slide. And then once you create the interface, it is very easy if you want to reuse. The predictability is very, very simple. The adaptability means, let us say you wanted to change those interface. And if the interface is instantiated 30 times, you have to change 30 times. But because of the interface is created in system Verilog, which is a feature of the system Verilog, if you change one line, it will change 30 times, right? So there are a lot of advantage to use. Now you assume you have a 2 block. One is called bottom 1, bottom 2. And this U1 and U0 is nothing but the instance, right? So it is instance, and bottom one is module name. So module name is bottom one, bottom two, U0 and U1 is instance. And then let us say this is your top, correct? It has a D1, D2, S1, clock is input, equal, and my select is a output of my top module. And they are connected internally. Now, if you see how they are connecting. So here also data one and data two, here also there is data one, data two. So data one of this bottom one is going as a input to the data one of the bottom two. Same way data two, output of bottom one is going as a input to the bottom two as a data two. So that means data one to output, data one to input connected. Means this is output, this is input. Same way, I think select is output. It is also going as a my select as a top interface, but it is also going as a input to this select. Right now, if you want to do all those stuff, so without interface, let us say, as just now I talk, right, there is an interface feature offered by the system Verilog. So if you do not use that feature of system Verilog, or if you use the Verilog right as it is, then you will define your module bottom two like this. So it has a clock, it has a select, it has a data one, data two, which is a 10-bit, and it has a result. So this is how you will define. But if you want to define just interface, what it will help us, you will define interface, again a keyword of the system Verilog, and then you can give any name. For example, your project name underscore int, project name underscore interface, or my interface, any name you can give. And then you will tell it has a logic. Look at, I'm not defining what is input and output. I'm defining just select, I'm defining data one, data two, and result, and I'm ending my interface. So what I'm defining is, I am creating one, let us say one group of the pin. Interface is nothing but the one group of pins which are connected internally. And I do not want it to connect explicitly, right? In previous case, if you see, I have to connect data one, data two, I have to connect like this. But in this case, what I will do is I will just define like this 2 lines or 4 lines, that data one, data two, result, and select. That's it. And once I define this interface, if I go to the next slide, right, without interface, this is how you will do. Bottom one, bottom two, this is instance U0, U1, right? Your data one, look at data one is connected from data one. So data one you will define as a signal. This signal will come like this, correct? Then data two will become like this, correct? These two are connected. And same way, select line is also going from here to, where is that, this select line, right? So you have to define, look at long line. Now we assume we have a 500 ports, right? So this line becomes so lengthy. Instead of that, if I have defined the interface, whatever I defined in previous, I have to define my bottom one and bottom two integration at the top level. This is which file? This is my top.sv file. Okay, so top.sv file has, I have to define like this. But if with the interface, if I have defined interface like this, only these 4 lines, right? If I define these 4 lines, I can define top.sv like this. So that means there is a one bottom IP, bottom one IP, which instance's name is U0, and I am telling instance 3, and this is also instance 3, for example. Then so whenever I'm defining instance 3, automatically it connect all this data one output of bottom one to data one input of bottom two, data two output of bottom one to input of data two bottom, and same way for the result and select line. So it will automatically. So I'm not bother or I'm lazy to define. I just define interface. So by defining interface, I have already connected my 4 ports. So compiler will take care, synthesis will take care. All the tools who are able to understand the system Verilog will connect these all lines. I do not define select, I do not define result, I do not define data one, I do not define data two. It is all comes when I say int3 or interface 3. And then whatever is not covered, clock is not covered, D1 is not covered, D2 is not covered. Why D1 and D2 is not covered? Because I cannot include it into interface. Why I cannot include into interface? because D1 and D2 is my primary input, which is going to the bottom one, but D1 and D2 is not going to the bottom two. So I cannot cover into the interface. Interface is nothing but group of signal which is communicated internally between two IP, which is called interface, and which is constant. Let us say I have integrated U1 and U2 like this in one module. In another module, if I integrate U1 and U2 like this, the connection is exactly same. Then and then I can multiply, I can reuse those interface across the different module. Okay, so then I will just connect the other signal apart from the interface. So when I will use interface, let us say you have a standard interface, right? Each and every IP will have a bus protocol. So for example, you have a APB protocol, AHB protocol, and each and every protocol has a 50 pins, 60 pins. And one protocol input will go to the output of the another input, or output of the another protocol or IP will go to the input of the next IP, right? It is vice versa. Input will go to output, output will go to input, something like that. So if you have those many interface, if you have a 250, 300, 400 IP at the SOC level, and you wanted to use a standard interface, because they are standard. Once you define that APBQ signal will go to the APB request signal of the next IP, it will be remain as it is. So if you have those standard interface, you define as a part of the interface keyword, and you can use by changing the number. That's it. The rest of signal you can connect like this, right? So these two lines is equivalent to this two line if you use the feature of the interface. Any doubt before I go to next slide? Okay, I hope you understood, right? So another important topic, I think maybe this is the last topic from my side for the system Verilog is assertion. Again, very powerful feature the system Verilog offer. The way you can use assertion checkers, right? So let us say, generally this is a traditional practice. I will write my RTL, A plus B, A minus B, E multiplied by B, and A divided by B. And then I will throw this RTL to the validation team, verification team. And that team will validate my RTL against my golden spec, against the architecture spec. But that cycle sometimes is very, very long. And when you find a bug into the late cycles, 2 months, 3 months, 5 months, for example, when we work on the complex SOC, our SOC cycle time is a 1.5 years. So when I start my spec to the GDS2 till I send the data to the factory, it will take 1.5 years. Now in this 1.5 years, there are a lot of RTL release happen, there are a lot of verification is happen, and there are thousands of test cases developed by the validation and verification team to validate or verify the RTL against the spec, right? And everything will happen in a staging manner. So there are some bugs that you do not want to keep that will catch by the verification team into the late in a cycle. The bug is catch in late in cycle, it is a heavy penalty, right, in terms of time, and we don't want to miss the market. So what happen, there are some assertion that you can code into the RTL, and when you run your RTL in the compiler, that compiler can understand, hey, this is the assertion, this is not part of my regular functionality, this is something extra functionality apart from the functionality, and this is used to check the functionality is correctly coded or not. If the functionality is violated against the assertion, then it will show a failure message in your log file. And if you search just fail string, you will come to know, oh, I wanted to code something, but I have coded something else. So assertion is very, very important. So now the RTL designer is also started writing the assertion. It is not only just we are writing the Verilog or system Verilog actual functionality, but on top of that, we have extended our things and we have started writing assertion. So for example, let's take this example. As per the spec, this frame, right? There is a one signal which is called frame. So frame is an active low. Okay. So as per the spec, when the frame is deasserted means actually it is going high, okay, which is called deasserted because it is active low. So when frame is deasserted, you need to check the LDP signal should be asserted. Again, LDP is also active low. Okay, so it was before high. So if the frame is going high within 2 clock cycle, as soon as the frame will go high within 2 clock cycle, your LDP also should go from high to low. If you meet this requirement, you are fine. If you do not meet this requirement, your test case should fail because you are not meeting spec. Okay, I mean, we have just hypothetical example. Right now, if I wanted to check these things in a Verilog, then it is very painful in terms of assertion, right? But if I wanted to check in a system Verilog, it's very easy, right? So for example, what happened in Verilog? Verilog, you will write this much big assertion. I think I lost the mouse. Okay, so if you want to verify the property of this spec, whether are we meeting, as soon as the frame will go high, the LDP will go low. So LDP go low within 2 clock cycle, not. So look at the frame is going high over here. So it will start from here. So my clock will start from here. So this is 1 clock cycle and this is another clock cycle. So between these 2 clock cycle, my expectation is LDP should go from low to high. So one possibility is here. So within first clock cycle, and one possibility is second. But if LDP is going high like this and then it is coming low here, okay, then you are violating spec. So if you want to write assertion, this many long assertion code you need to write in Verilog. Okay, so in Verilog, what you are telling at the positive edge of the frame. So when the positive edge will go, at the time check something. What do you need to check? LDP check. Let us say begin, and you have given name LDP check. What you are checking? When the frame go high and clock becomes positive. So when frame go high means at this time. So at this time, frame is going high. So after that, what is the first clock? This clock. At that time, you will check whether the LDP is going to negative edge. So whether it is going here or it is going here. If it is going here, disable this check. Don't enable. If you enable, then it will throw error. So disable this particular check. And you repeat this 2 times. If it is not happen, then display LDP check is fail. So this is how you have to write. And then once you write a fail, then you disable the LDP check because you have throw this message to the user. Hey, you have not designed as per the spec and you have to change your RTL. Same thing if you want to do using system Verilog, right, which is a more powerful in terms of assertion. You will write only single line, or I would say 3 lines. Instead of these 10 lines, you will write only 2 lines. What you will write at every positive edge of the clock, and when the frame will go to the high, I think which is rose, or I think I need to write rise, RISE. Okay, so when it will go, frame will go to the rise. So when frame is going rise, within 1 or 2 clock cycle, make sure the LDP should also fell down. Within 1:2 means within 2 clock cycle, LDP should fall down. If it is not happening, display LDP's check. That's it. So if you write single line or 2 line, your assertion is done in system Verilog. While in Verilog, you have to write this much lengthy code. Now you consider the more complication scenario. When frame goes high, LDP either go low, either in first or 2 clock cycle, or 5th and 6th clock cycle. How complicated this becomes in Verilog. But how easy it can be, right? Either 1, 2, or you can write 5:6, yeah, and you are done, right? So a lot of enhancement happen in a system Verilog that will help the test bench as well. That will help also the assertion, that will help the RTL designer, that will help the microarchitecture team to validate early and neatly, right? So this is another example of the system Verilog, which has a strong and very neat way to write the assertion. Okay, so with these slides, I'm at the end of my presentation. But if you want to have any question, query, or if you want to share your thoughts, we can talk.
I am having one question related to system Verilog. That at DDU, our students are doing simulation for system Verilog using the tool that is EDA Playground. It's an online tool which
Right.
supports the syntax for the system Verilog,
Mm-hmm.
but it is having some limitation. So, are you aware with any EDA tool, freeware EDA tool, which can support the syntax of system Verilog?
I don't know the free, but I know the paid one what we are using at our company.
Okay.
I need to cross check if any free tool I can point
If
you.
any evaluation version of that tool is available, then also it may be helpful to our student.
That's right. Yes. So generally we are using the Synopsys tool
Okay.
for this compilation and verifying and everything.
Okay.
But that is a license one. But yeah, there will be some tool available. It's just matter of
Yeah.
finding it.
Fine. Okay. Any questions from participants related to this session? Please feel free and ask the questions. Okay, so I think there is no question from the participants. Thank you, Keyur sir, for delivering such a wonderful talk on the topic digital design and modeling. It was a really very informative talk. You have start from the scratch. You have discussed the first of all the ASIC design flow. Then you have covered the various modeling techniques of Verilog. Apart from that, you have also discussed in detail the blocking and non-blocking assignment. Then you have discussed the limitations of the Verilog and how it should be overcome by using system Verilog. I thoroughly enjoy your session. I hope the participants have also enjoyed your session. Thank you very much for delivering such a wonderful talk. Thanks again.
Thank you very much to all, everyone, and Dr. Mithas. Thank you very much. It is honor to have and discuss with you. Thank you.
Thanks. Thanks. Now, dear participants, as per schedule at 3 p.m., one lab session is there that is based upon Verilog. So in that, we will discuss various modeling techniques of Verilog by taking some examples, and we will also demonstrate that example by using the EDA tool like Quartus 2, that is which is of Altera, and Model Sim, which is of Metagraphics. Right, so we have put too much effort in order to prepare the lab session. Right, so please remain present at sharp 3 p.m. today to attend the lab session. Yeah, thank you all.
Thank you, everyone.
Yeah, thanks, Kier.